graphs of factorized cubic equations or functions. This is where they start to get a little bit interesting. We can do some kind of roller coaster graphs, have a bit of fun with it. Nothing too scary, it's not actually that bad. So as we would with quadratics or just about everything else we found, we may factorize, find y-intercepts, find x-intercepts, and we do our best to find as many coordinates as we can to then start sketching. We may have turning points, we may have points of inflection, we may have none, but we just do everything we can to label what we can, and we go from there. So I've just grabbed 5 kind of common forms of these cubics, so we can see our first example, 2x bracket x plus 1 and x minus 2, x-intercepts at -1, 0 and 2, so same as everything we've done, we have that flip of the sign if we're in a bracket. Don't forget an x out the front of a bracket is a intercept through the origin, so 0, 0. We may have dilations, as you can see in example 2. They don't really impact it too much. We're not finding kind of all the turning points in this case. You do that a little bit down the track. But we can see that we have a turning point on the x-intercept here, and that's really important because that squared value is making it turn around. It is just touching the x-intercept at 1. So be really careful with that. That's actually giving us a bit of information as to what's occurring. And of course, -2 is our other intercept there. Our third example here, we have an x-intercept at 1. The reason we don't have other x-intercepts is that x squared plus x plus 4 cannot be factorized. Its discriminant would be less than 0, therefore there's no further solutions we can find from that. We then have our point of inflection form, so 2, 3. We did that a little bit in the last lesson, so check that out if you're unsure. And don't forget we may get reflections across the x-axis, so that's the first graph again. It's just been reflected across the x-axis, so you can see it's been flipped the other way around. It can be difficult to work out how far these kind of dips and rises occur. Basically, the distance between your x-intercepts and any dilation will impact the rise and fall of your function. So you don't have to be perfect, you're just labeling coordinates and doing the best you can at this stage. Okay, so the first part of this is pretty easy. We just state what our x-intercepts are, so -1, 1, and 2. So I'm going to mark those here, here, and here. If I wanted to find the y-intercept, I can multiply 1 by -1, and the result of that by -2. So that actually comes out to be +2. Oh no, and I need to multiply by this 2 as well. So it's kind of expanding, but you don't really have to expand the whole thing. Just multiplying the numbers in your brackets and the value at the front. So +4 is what we're talking there. So that's our y-intercept for this one. We don't have a reflection, so this graph is going to be looking like that, and you can already see we've kind of got a sense of the shape from there anyway. So let's see if I can I get so nervous doing these. Yes, pretty good. I bet I made a silly mistake somewhere here, but anyway. I'll check it later. That's a pretty good graph, I'll take that. So you can see our kind of dip at the bottom between 1 and 2 isn't as great because as our rise, where we've got our y-intercept, just because of our distance between those x-intercepts is a little bit of a guide. But that's it. It's probably not perfect. It's probably not even good, but it's close enough. So we can't crack into sketching this straight away, but we can take out the common factor of -x squared, giving us x minus 4, so just be careful with those signs. That will give us x-intercepts at 0 and +4. That 0 value is also our y-intercept obviously as well, so I mean you could prove it by subbing 0 back in for x and you'd get 0, but we know we've got an intersection here and over at 4. Now because of this squared here, really important, we have a turning point at that x-intercept. So, because we've got this negative as well, we're going to, oh man, this is going to be hard to sketch. Okay, come down, turning point, over here. Oh, it's so bad. All right, wait, maybe from over here. Oh, it's better. All right, I'll take that. All right, there you go. So that's all we can do there. Key feature is that squared. It gives us that turning point at the origin. So just be really careful with that. And the negative is a reflection. So we've done quite a lot of long division and synthetic division. I'm just going to show you that for a little bit. If you want to go through that, feel free to do so. There's dedicated videos to that content, but I'm just going to focus on the sketching here. So I'm assuming that you can correctly factorize these cubics. So let's go and look at the graph at the bottom. So getting a little fancy, let's go with 2, -1, and -3 as our x-intercepts. So let's start marking those. So 2's here, -1, -3. We know from the original function up here that our y-intercept was -6, so I'm going to mark that here as well. And again, from the original, we can see that we don't have a negative in front of our x cubed, meaning there's no reflection. So this is going to be one of those kind of shapes again. All right, let's see how we go. No, it's not great. That should have come down a bit further, but that's okay. And again, just labeling everything we can. Don't know if the rainbow pen's doing me good work today, but let's stick with it. So, not ideal. Probably, this one should probably come down a little bit further, but that's okay. I'll just leave it like that. Obviously, on a test, you want to do the best you can, but smooth and continuous, labeling coordinates, that is a big tick. Getting the shape generally right is fine as well. Looking at our next graph, we've got our x-intercepts of -2, 1/2, and -2/3. Going back to our original equation, there is no negative out the front, therefore there's no reflection, and we can see that our y-intercept is going to be -4, so we can do that pretty quickly. So -4, I've got a -2, yeah, 1/2 is here, and -2/3, let's go about there maybe. Alright, so down. Oi, it's pretty hard to look at. Okay, labeled everything. It's not a great sketch. I find this quite hard to do on the computer, but there you go. Again, just labeling coordinates, thinking about the reflections that you have, where your turning points may occur. You're not expected to be perfect with that yet. You do learn a thing when you do calculus to find those actual turning points. It sounds really scary, but it's actually not too bad. If you're finding this tricky, again, use technology. CAS Calculator or Desmos is great for this kind of stuff. And I hope I haven't gone too fast. Good luck. Keep at it.